Okay, so let's start. So this is the story. Just you have to think about this as a story, not as something that you have to remember as a formula or some strategy to solve some problem. So this is all about the story that mathematicians have worked on about how to understand the space, how to understand some structure of the space. So let's summarize what we have discussed last time. That is about when you have a vector field on two-dimensional space. So these PQ are two-dimensional two-variable functions which constitutes x and y coordinates of the vectors in the vector field. And we have a curve C inside of two-dimensional space. And if I have to be more specific, then I should say this vector field is defined on not only on the curve, but also the inside of the curve. Okay, that will be important when I discuss when we discuss about the potential functions and so on, some theories about potential functions. So anyways, for now, let's think about this vector field is defined on entire space, entire two-dimensional space, and this C is a parameterized curve which is closed, and we assume that this is oriented counterclockwise. Then, first of all, we can say that the line integral over the closed curve of this vector field is given by the double integral on the domain D, and also I should say that the C bounds the domain D, which is in two-dimensional space, of rotation of F, which is Qx minus Py dx dy. So to be concise about the notation of F, I can say that this is equals to line integral of vector field, which is written in this form, is equals to the surface integral or double integral of scalar function. Okay, so that's one of the theorem, and then we call this as a Green theorem because it's the Green's credit. The credit to Green, who first discovered that this holds. And the second one is that if we say that our orientation of we have an orientation of a curve, and also according to that orientation, we can fix a normal direction of the curve. So, but we assume that this orientation is fixed as counterclockwise. So this n will be a function from, let's say, function from a point on a curve C to a vector. So this is a vector space, and this C is the image of this parameterization C. So I'm going to write this way. Okay. So this is a normal unit vector field on the curve C. Okay. So then we also said that the line integral of this function So I'm taking the inner product with the vector field f and the normal vector field n. So basically, I'm getting a scalar function, and I'm taking a line integral of the scalar function. Okay, is that same as taking a double integral on divergence of f, which is given by px plus qy dx dy. Okay, so also I can write this in, well, I think maybe I don't want to write it in this other format because this n direction matters with the parameterization of C. So I'm not going to write in a concise form, but before I move on, let me denote that this is called divergence of f, and this is called the rotation of f. Okay. So first one is called Green's theorem, and second one is called, there's no name for that, but somehow it's a two-dimensional version of divergence theorem. Okay.
Professor,
Yes.
I think it is reasonable to add the precondition that the vector field f is a function of C class of C1.
It's a function of what?
I mean, it is reasonable to add the precondition that the vector field, I mean, P and Q is the class of C1.
Yes. Right. So. Right. So very good comment. So remember how we proved this inequality, that the essence of proving this equality is that we use the mean value theorem, the mean value theorem on the partial derivatives. So when you want to use the mean value theorem, you should assume that the derivative of a function is continuous in order to find some tangent slope is equal to the average slope along certain intervals. So same holds for entire argument. So we said that this P and Q satisfies, if I fix one of these variables, then if I assume that this P and Q are a single variable function on one single variable in P and Q, then I should able to use the mean value theorem. So in order to use the mean value theorem, as Hyun-Gyu said, that we need a condition that this PQ has continuous partial derivatives for every variables. So the remark is the function PQ must be continuous, must admit continuous partial derivatives, which means that all PQ derivatives are continuous function. So when I say that these four functions are continuous, I'm talking about the continuity on the multivariable function. These are multivariable functions. Okay? So we have to go back to the continuity of multivariable function to really know what this means. Since the proof of the equalities requires the mean value theorem. I'm using capital L to emphasize for PQ. Okay. Right. So any other questions?
Does that mean notation F?
Notation of what?
Over QX minus P1.
Here? Rotation of F, right? ROTF. Okay, so what we're going to do today is going to generalize this argument to three-dimensional space. So far, everything is in two-dimensional. We're going to think about the similar thing could happen on the three-dimensional space. For example, I'm going to generalize the vector field to a three-dimensional vector field and curve on the plane to curves on the three-dimensional space. And also the domain D, which bounded by the C, will be the surface in three-dimensional space, which is bounded by the curve C. So before we make an argument, let me give some definition or notation about some symbols. Let's say I have three-dimensional vector field. So it takes each point to three-dimensional vectors, and these vectors have coordinate PQR, where PQR are actually three-variable functions. Then I define a curl as this nabla. So this inverse triangle is called nabla times. So this is actually the cross product symbol, cross product with F as some three-dimensional vectors. I'm not going to write it right now because I don't really remember the curl formula, but there is a way to remember this. And also this symbol. So I have an inner product with nabla and F, and this will become some scalar number. So I just mentioned the name for these. So this is called the curl of F, and this is called the divergence of F. So how do we remember this curl and divergence? So remember this notation. Whenever we put a nabla, it appears many times in a physical context. So we can remember this as a vector of operators. Vector which has an operator on each component. Okay, instead of having a number on each component, you could assume that this nabla is a vector whose components are operators. You see, this del del x doesn't have any functions attached to it. So if I put a function symbol on the right-hand side of these operators, this becomes now a partial derivative. But before we put f symbols, this just gives you some kind of procedure that you're going to take a partial derivative. So once you accept that notation, then the curl is, symbolically, it's a cross product of two three-dimensional vectors. So I can say that this is equals to determinant of I, j, k of, first, the partial derivative of x. So I'm going to abbreviate as this dx and dy, dz. So that's the components for the curl, the nabla here. And we take the PQR, which is the component of f. And think about what we get after we take the determinant here. So first of all, the I component are having the coefficient ry minus qz, ry minus qz I. And how about j? So j has pz minus rx j. And then k is qx minus py k. So we have seen this qx minus py in two-dimensional versions. So there is a reason why this qx minus py appears. It's not a coincidence, because we're going to see that this actually, if you have a special case, then it actually goes back to this original two-dimensional case. So anyway, this is our curl. So I'm going to write that here. So ry minus qz and pz minus rx and qx minus py. And let's think about the divergence. So you can consider, again, the nabla as a vector. So I'm going to take operator vector and take the inner product with PQR. And you perform this inner product as if those are the numbers. So I put this P to the operator del del x, so that gives Px, and then add with the operator del del y attached to Q, which gives Qy, and then add with the Rx. So that's our divergence. So that's how you remember the curl and divergence. Okay. So we need this fact. And what we're going to prove is the following. So first of all, Stokes' theorem. So unlike the green theorem, we should assume that the orientation is not always fixed, but you have to give an orientation. Let's say C be a parametrization of a curve. So to the r dimensional. So be a parametrization of a oriented curve. So which means that you have already an orientation of a curve. So you know where to move along the curve. So I'm going to call this C as a capital C. Okay, so this parametrization is a small c, and this curve C as a set is a large C. And then let S be a oriented surface on R3 whose boundary is C. Now, I'm going to give a picture here. So let's say I have this picture in three-dimensional space. I'm going to call this surface as S, and I'm going to call the boundary of this surface as C. And C has an orientation. And S is also an oriented surface, which means that we can give an orientation. But we said that whenever you have a surface, actually it applies to any dimensional manifold in a higher dimension. But if you have a surface in three-dimensional space, then you can give either one of two orientation. In this case, you can give an orientation as an upward or a downward. Okay. But in the Stokes theorem, you have to fix your orientation of a surface. I mean that orientation is the normal direction, how to give you the normal direction to the surface in a continuous way. Since we have an orientation of a curve, the orientation of surface, which applies to the Stokes theorem, is fixed. How you fix your orientation is the following. Listen carefully. So you walk along your curve C, okay? You walk along your curve C, and then your head is pointing to the normal direction of your surface or the orientation of a surface, then your left arm must be pointing to the surface S. So in other words, the orientation of a surface according to the orientation of a boundary curve C is the direction that your head is pointing when you move along this curve C and your arm is on the left side, your left arm is pointing to the surface. So I'm going to draw a person moving along this curve C. Imagine that you're moving along this curve C. In order to have your left arm pointing inside of the surface S, your head must be pointing to the upward in this case, right? If I have a same set S and same boundary C, but what if my orientation of orientation of a curve C is opposite? If I have this orientation, then in order to have my left arm pointing to the inside of the surface when I'm moving along this orientation of C, my head must pointing downward, right? So in this case, the direction where my head is pointing at is the normal direction of the surface S, which is the orientation. And in this case, the direction where my head is pointing is the direction of the normal direction, which is the orientation of a surface. Okay? So there are two directions of orientation of a boundary, and that accordingly gives you the orientation of a surface. Okay? So I'm going to write that in the simple words. So SB-oriented surface under whose boundary is C. Let N be actually the D orientation of S with respect to the orientation of C. Okay. Okay. So there are many things going on in these three words, with respect to. Okay. So that's what goes on. But just I explained here. So the conclusion is that if I take a line integral over this curve inside of three-dimensional space of the vector function vector field. So I should mention that the vector field is here. So this F is, let's say vector field defined on the surface S. Okay. Then if I take a line integral over this curve C, then it is equal to the surface integral over the surface S of function F inner product with this orientation N according to the orientation of C. So you can simplify this notation, right? So you can rewrite this as vector field, the surface integral of a vector field. So when I say this ds as a vector component, then what I mean by is that the direction of its orientation of a surface S, and then the increment ds is the same amount as the norm of this ds vector here. So I'm going to put a parenthesis. So this is the Stokes theorem. So whenever you say about the Stokes theorem, don't just remember this formula, because there are lots of things to explain in this formula. Because whenever you take the line integral of a vector field, you should mention what direction of your what direction is your curve C? In which direction you're taking the vector field, line integral of a vector field? And also, when you talk about the surface integral of a vector field, in which orientation, in which normal direction you're taking a flux? So it's not that you take a random direction of this curve and random orientation of a surface. You have to match this orientation of a surface and then orientation of a curve equal according to these pictures. Okay. Let me say it again. So let's say you fix your curve orientation of a curve. Then your orientation of a surface, which is the normal direction, is where your head is pointing when you move along the orientation of a curve C and you want your left arm inside of the surface. If your orientation of surface is fixed, suppose that your orientation of surface is fixed, which means that you know which direction you want to take the flux, then the orientation of a boundary curve, the curve C, is the direction where you should move to when you put your head direction to the orientation of a surface and you want your left arm to be in the side of inside of the surface. So for example, if you had your orientation upward here, then you want your head upward, but you also want your left arm put inside of the surface S, and then you have to decide which direction should I move. So in this case, you should move along this direction in order to have your left arm inside S. But if your head is pointing downward, then in order to have your left arm inside, think about the three-dimensional image. So your left arm, in order to have your left arm inside of S, you should move it backward, this direction. Okay? That's the orientation. Again, let's talk about one more thing. So this is the Stokes theorem. And then the next one is called the divergence theorem. So the situation on divergence theorem is a little bit different because now you want to generalize this argument to the three-dimensional situation, right? You had a closed curve which bounds the two-dimensional space. If you generalize the dimension, then the curve is one-dimensional thing that bounds to two-dimensional thing. Then we need two-dimensional thing that bounds three-dimensional things. So we need a surface which bounds the three-dimensional space. So the surface that has no hole, which means that it bounds completely a closed area, closed region in three-dimensional space, is called a closed surface. So let S be a closed surface which bounds a region, let's say V, okay? So, and then also let's say F V to R3 as a vector field which defined inside of this volume that's bounded by the surface S. And I'm going to assume this S is also an oriented surface. If it's not oriented, then we cannot determine which region is bounded by S. And now S is oriented, so we can decide which orientation that we can choose to take the flux. But I'm going to fix my orientation of S so that the orientation is the direction that gives the outward direction of the volume. So which means that if I have a closed surface like this shape, then I know that this S bounds this volume. So I'm going to define my orientation of surface as an outward direction. Okay. So this is going to be my orientation. Let N be an orientation of S, which gives outward direction. Okay, I was hoping to write one more sentence, but I don't have space there, so let me write it here. So then the conclusion is that if I take the surface integral of the vector field along that orientation, which gives the flux over the surface S, then this is equal to the triple integral of divergence of F in the volume V. So I'm going to write volume V, integration of volume V this way, so it's dy dt. Right? So if you don't understand anything of this, please ask right now, because the theorem or any properties or statement in the mathematics should be understood without looking at the proof. So proof doesn't give you insight, okay? So it's an advice to anyone who are interested in mathematics or anything to do with the mathematics. You should not look at the proof to get an insight. You should have an insight by looking at the theorem and or think about the situation in a concrete examples. So I'm saying the example not that you take as a problem solving. Just think about drawing a pictures or imagine in your head what's going on. So, and also the insight doesn't. You cannot get an insight by looking at the formula. Yes, question?
I have a question.
Yes.
You explained the orientation of N
Mm-hmm.
by using the equal and left side.
Mm-hmm. Mm-hmm.
I think it is same with the right side hand theorem.
Right side hand theorem. Yeah, it's a kind of similar, but this is simple, so simple so that you can just simply put your one hand and then think about this orientation. But what if your surface is very complicated and it's upside down and sometimes, and you don't really know what's going on in some cases?
Then they're all different.
What do you mean by what is different?
They're all different by right-hand side and explain.
I'm simply saying that you cannot use the right-hand rule to find out the orientation on a complicated surface. So this is very simple surface that you can think about as if it's just a plane, and then you can think about this circle boundary as somehow has an orientation in one clockwise or counterclockwise direction. So you can think about it as a right-hand rule to point out the normal direction. So yes, you can use the right-hand rule. So it's actually the same as the right-hand rule, but this is simple surface. But yeah, what if you have very, very complicated? Well, it's not really that complicated, not even for this example, but let's say I have this kind of surface. So let's see this the surface here, right? So you want to look at, if you want to make a whole picture in one big circle, then you can use the right-hand rule. But what if it's so big that you cannot use one, you cannot even look at one big picture of the surface, and then you want to use the right-hand rule, and then, okay, so I'm going to use this small part here, and small part there, and small part there. And then if you're looking at this part, and okay, right-hand rule looks like this, and then you sum up here. But if you're looking at this picture, now, okay, use the right-hand rule here and sum up here, then it doesn't make sense because now normal direction is opposite. So it's up to you to use your right-hand rule or right-hand rule or this kind of situation. But I'm simply saying that right-hand rule may not give universal tool to find out the orientation in the larger or complicated situations. But you're right, you can use the right-hand rule. Yeah. Any questions? Again, so here I said that this orientation is an outward direction, but you can use the inward direction too. If I take the inward direction as my orientation of surface, then what is my V? What becomes my V? V, the region that S is bounding. So if I take the inward direction instead of outward direction as my orientation of surface to find out the surface integral of the vector field, then according to this, so if I take the inward direction as an outward direction, which S is bounding, then V is not anymore inside of the surface. V is the outside of V, which is the infinite area, infinite volume outside S. Then I can use the inward direction. But in order to find a surface triple integral over this infinite region, then we need an improper integral, and things get complicated. And we don't want that. And also, what we are doing here is just finding the flux over the surface S. So if you really want to find the flux inward, then just put the negative when you take after you take the flux to the outward direction, right? So think about the situation here. So we have a line integral becomes a flux, and which means that you can transform your work as a flux, and also you can transform your flux to some divergence, so triple integral of some divergence. There should be some physical meaning to that whenever they use it in the physical context. And before we really dig into this proof of Stokes' theorem and divergence theorem, let's compare that with the previous two-dimensional version of these Green's theorems and the divergence theorem. So what does Green's theorem tells you about? So we have a plane in xy space, and we had a curve in counterclockwise orientation. And we had everything in here in the flat surface, but we had another axis now. Let's think about translate everything that we've done in the two-dimensional space to the three-dimensional space. Then the curve is now becomes the same curve, but it becomes it's a curve in three-dimensional space, but it's flat in xy space. So everything now becomes flat three-dimensional curve. And we had a vector field defined on this two-dimensional space Now, if I enlarge, if I view that three-dimensional space as two-dimensional vector field as three-dimensional vector field, then now it becomes, let's say, as I said, this function doesn't have to be defined on every plane, so it only has to be defined inside of the region that's bounded by the surface, curve C. So I'm going to call it region D. So this vector field is now become a three-dimensional vector field, which takes a point inside of D. Now D is now considered as a flat set, sits inside of three-dimensional space. So it's going to be xy0 maps to pq0, right? You don't have a z component for the vectors. So what we have discussed as of inside in the Green's theorem is that if you take a line integral in two-dimensional space, but you can exactly take same line integral in three-dimensional space, so that you can say that this three-dimensional vector field is taken as a integrand, and then this curve is also taken in three-dimensional curve. Okay, so then this is equals to p dx plus q dy plus, now we have zero components, so 0 dz, so that disappears. So that's the left-hand side of the Green's theorem, and exactly the same as in the Stokes theorem. And what happened in the right-hand side of the Green's theorem? We know that this is equal to double integral on D of the rotational vector field, which is a rotational vector field, pq minus py dx dy, right? So that's the Green's theorem. But what does Stokes theorem tells you about? So Stokes theorem says that you can translate your line integral to surface integral. You need to know what the orientation of your surface. We had a counterclockwise direction of the surface. So what is the orientation of this D, which is bounded by C? What's the orientation of D? Is it upward or downward? Upward, yes. So this is our orientation. And is orientation a constant vector field? In this case? Generally, no. But in this case, does orientation change? No. It's always equals to 0, 0, 1, right? So I'm going to apply that to the here. So it's going to be a surface integral of a vector field. The curl of the vector field curl f, and I'm going to take orientation as 0, 0, 1, and then I'm going to integrate over the surface S. Okay, that's the Stokes theorem, right? So let's think about what happens here. Let me maybe right here. So we had a three component for the curl. But when you take the inner product with 0, 0, 1, everything disappears except the last one. So what was the component for the last one? Qx minus py, right? So we have that one and qx minus py, and we're going to take a surface integral. Okay? So compare that with this. Since we have a surface S, or I mean the D, this ds just the conventional notation for using in the surface integral. So D is already in the xy plane. So I'm going to use x and y as coordinates for parameterizing D, right? So ds can be just, I can parameterize D without using any transformation. So I don't need any Jacobian to multiply. So this is equals to simply integrating over dx dy, right? So that's here. It's the same thing. So you can use the Stokes theorems to prove the Green's theorem. And how about the two-dimensional version of divergence theorem? So you had a xy plane here. So we had a curve C. And in two-dimensional divergence theorem, we had these. I want to find a flux that goes outward of this curve C. Okay? Then, but we can think about this as a xy plane which has z-axis, additional z-axis. So that's that. That's the end of the theorem statement. And then this is another remark. Sorry. So this is another remark. So recall that if I take, so this is n, okay? If I take the flux outward, sorry, maybe can I can I make it as a three-dimensional volume? Maybe. Well, z component is. Well, if I really want to make it as a generalization, then I can make a cylinder with the same base, and we have a cylinder, and with, let's say, we have cylinder of height 1, okay, height 1, okay. So I'm going to generalize my vector field into three-dimensional vector field. How I can do that is just trying to make every vector field in a parallel direction to the vector field defined on xy plane. Sorry that I have to use another color here. So the yellow one is for the vector field and green one is for the normal direction of the curve. Okay. So these are the vector field. So let's see. My vector field was originally two-dimensional, but I'm going to add 0 component on the z direction so that I can enlarge that to the three-dimensional vector field. And let's see. Okay. So and then Green's theorem. Well, I think it's hard to generalize because I have to increase the dimension, right? So I was trying to give an example. I mean, I'm trying to give an insight how to generalize two-dimensional thing to three-dimensional. But let's leave it like this. So let's not think about how, like making an arbitrary, like making an ad hoc picture here. But instead, let's think about what this means. Okay. So in the two-dimensional version of divergence theorem that we had, this line integral is same as the divergence of function d x dy here. So this is a flux, right? This is a flux, two-dimensional flux, which flows outward from the boundary of the domain D. And this gives, so what does this give? So it kind of measures how much of this vector field expanded over the domain D. So total flux over the closed curve is measured by how much of the vector field expands the particle, the distance from the particle, or expands the volume inside of this domain D bounded by the curve C. So if there's no expansion inside of the curve, inside of this curve, then exactly the same amount that goes inside of the curve will go outside to the curve. So flux will be 0. But if there's any expansion inside of the curve C, then some like positive expansion, then any flux goes inside, flows inside of the curve C, will be expanded inside, and then more will come out, right? So we have a positive flux. So I would say this is not exact correct word, but it's in the quote. This is the how much of the particle have expanded inside the curve C. Okay, so that makes sense. So if you compare that with the divergence theorem, which is up there, so you have same situation. You have, instead of two-dimensional vector field, you have three-dimensional vector field. You want to find out how much a vector field flows in and out, okay? Because you have a closed surface, right? So you have no missing part, okay? So everything goes in should go out. But if there's no expanded thing inside of this surface, then exactly the same amount flows in will go out. But if at some point there is some expansion in divergence and the net expansion is positive, then what flows in will expand it and then goes out more. So you have positive flux over this closed surface. That's exactly the same, exactly what this formula tells you about. And ideally, the situation is exactly the same in these equations. So you have to understand the meaning of Stokes and divergence theorem, and also you have to understand the condition where you can use the Stokes and divergence theorem. It's not important to how to apply your Stokes theorem and divergence theorem to calculate some weird problem that the problem made for just because to test you in a midterm or final. So if you have any suspicions or doubt or misunderstanding or not a vague understanding about the Stokes and divergence theorem, ask right now, because this is the time that you have, the first time you encounter any theorem or statement is the best time to fully understand that concept. Okay? At least you should know that you should have a feeling that you kind of understand what this is going on about. So if you have no idea what I'm saying about, then I can explain the whole thing again to make you understand. So at least you have to have a feeling about understanding these two theorems. Just freely ask if you don't understand any of this. Yes.
I can't follow about, I didn't understand comprehensively about the Stokes theorem, that the equation that the integral of closed surface, closed curve C of vector field F times ds vector is equal to the double integral of vector field dot product, the normal vector and times ds. I mean, so I'm actually confused about the left-hand side of the equation, the integral of closed curve. I mean, we calculated the integral of closed curve, but the Stokes theorem tells us that it is equal to the double integral of surface, and still I don't get it how this equivalence works.
So you're talking about how intuitively you could understand the equality is true.
Yes.
Okay, so that's a good question. So at least you understand the left and right side of the equation in a separate way. So you know that this is left-hand side the line integral and right-hand side is the surface integral. Okay, so far it's good. Okay, so as long as you understand the terminology of this formula. So I'm worrying about there could be someone who don't understand about this terminology yet. So I will wait a few more minutes to have other questions, and then I will going to answer your questions. Okay. So anyone else? No? Anyone from Zoom? You can type your questions or just type anything. I mute your voice, so you have to type.
Professor, I have
Yes.
one question.
Mhm.
This is much more simple question
Mhm.
about the picture that you give us the example.
Yes.
Yes. In the picture, one person walks through the curved seat
Mhm.
and along the curved seat, and you said that left hand goes into the surface, right?
Yes.
Then that the hand that go into the surface means that this left hand is somewhat somewhat. I thought maybe it could be the tangent line or tangent.
Tangent.
I mean, in that picture, the curve is like this shape.
Uh-huh.
Then you mean I'm quite confused that what it means the inside of this.
Inside of a curve. Okay, so good question. So that's very good questions. Probably many people should not yet fully understand what that mean, what's going on here. So, all right. So let's say we have a surface. So or maybe some boundary of a surface, and let's look at this one. So we have this picture, and I can draw a tangent plane to that point. So supposing that my plane would be extended a little bit more so that it has more sides there. So I'm going to put a tangent plane right here. Okay. So tangent plane has two normal directions, two perpendicular directions. One is to this word or other. Maybe one is this word. Okay, and the other is that word. Okay, there are two directions. Let's say I'm moving that direction. Okay. And so choose your orientation. Let's say I pick my orientation to be this one, and I'm moving this way, this direction. Then, okay, so this time is the good way to use the right hand rule. Okay, so as Suo said before, you can say that your all right. So if we move this direction, there are third direction that is mutually perpendicular to both of these two vectors. So I'm taking this. Okay, these two vectors. This is my head is pointing to head, and this is the walk direction. And my left arm should be pointing to where? The cross product, right? Or not, maybe is it cross product? Cross product in which direction?
Head and walk.
Head and walk. Head and walk.
Head first and then cross product. And it will be the left-hand side.
Head and walk. Yes, right. So this is the left arm direction, right? So you see these three vectors are usually perpendicular to each other. So walk direction is perpendicular to left arm direction, right? And your head is also the perpendicular to this direction. So the point is that once you decide any of these three vectors, the other one is fully already decided, right? Because your body is already oriented in a positive direction, okay? So in this way, your left arm is outside of the surface, okay? If you want to put your left arm to the inside of the surface S, you have to walk backward, right? Because head direction is already fixed, okay? You should put your left arm to the inside of the surface. This is not the way you can put your left arm inside of the surface S. Okay? So you have to decide one of these directions. Okay? If you fixed your head direction, then you can decide either walk direction is this direction, that direction. But according to that direction, your left arm direction is fixed. So there's only one choices, whether your left arm is inside of S or outside of S. So the walk direction is fixed according to the direction of your left arm. Okay. Other way around, suppose that your walk direction is fixed, then you have to decide which direction of your head is pointing to. If you put your head to this orientation, then your left arm is pointing outside of S. So you should not have your head that direction. You should have the other direction of your head inside. Okay? So maybe it's, I never tried this one in the formula, but maybe if you want to use the right-hand side rule, then let's see, your left hand direction must be head walk first, right? So head walk equals to left. So this is the cross product, right? So if you want to use the right hand, okay, so maybe I take back that the right hand rule is not as useful as this one. Maybe it's very useful. So if you think about your head walk direction in head walk direction as your direction that your forefingers are pointing to, then what your thumb is pointing to is the left arm direction. So you want your thumb direction to point inside of the surface. So that could be one way you can remember to decide the orientation of a surface. Okay. So I always try to give you intuitive proof and also the concrete proof. Concrete proof makes you feel better that the theorem is mathematically concrete, it's logical, so you can use it. But it doesn't help you to give an intuition, get an intuition. So I'm trying to give an intuitive proof. That proof is really not a proof, so it's like a pseudo proof, but gives you intuition. All right, so let's start with Stokes' theorem. So what I'm trying to do is trying to subdivide our surface. So let me put a proof for Stokes' theorem. Here is our surface. And I'm going to fix my orientation of a curve and the surface. So in one direction. So I'm going to fix my orientation of a curve outside a boundary of surface in this direction, and also the orientation of the surface in this direction. Okay, so this is my n. Let's subdivide. Okay, like this. And think about one of these subdivisions. Okay. What we do when we take the surface integral of this function vector field, which actually gives the flux over the surface S, is trying to get a flux over these small pieces of the surface in that direction and then add them all, right? So let's think about what's happening in these small pieces. So I take this piece so small that the vector field is almost constant over that small piece, and the normal direction is also constant. Okay, so I'm not going to worry about whether the orientation is changing or so on. So at the small piece of S, the N, F, and what else? N, F are constant, almost constant as a vector, okay? And let's say small piece is delta S. Delta is almost a what? So you have a curved surface, but if you take enlarge to this surface, it almost looks like a flat surface, like a flat plane, almost a flat planar piece. Okay, so assume that that picture is enlarged so that we are looking at the flat perpendicular parallelogram, and which points that direction. And also here we have a constant vector field F over this small side here. Okay. Now, what's the flux? The flux over delta S is how you get the flux is. F dot product and right. That's your flux. Right? So you're going to add this everything. And now, before we add, let's think about what happens when you take a line integral in these directions. So since it has a boundary, see? So let's say we call this boundary again as a C here, okay? But that's not the same C there, but anyway. So this, what happens when I take the integration over this curve C? So in fact, you have to go through all complicated computation about this curve, parameterization of curve, and the coordinate function, vector field F, and so on. But let's make it simplified. Okay, let's make it simple. So the way you can make it simpler is that you can, you don't have to, if the plane is a little bit slanted, which has a slope there, you'll have to think about this slanted surface, slanted planar surface, right? You can just simply rotate this whole thing to the xy plane, because the flux doesn't change at all by rotating, okay? So let's make this picture simpler. So let's say I'm going to make it flat on xy plane, and that way I take my normal direction n, and also the vector field is, sorry, so I think looks like this direction is perpendicular to the surface, right? This parallelogram, right? So maybe I should change back to here. So, okay, so this direction is my f. So f is also rotated, okay? So this is, let's say, x, y direction, and this is z direction. So I make it flat by rotation. And then what? Let's try to think about what happens when I take a line integral. What do I get? Think about Green's theorem. Think about Green's theorem. We said that the Green theorem is about two-dimensional thing, but we can embed it into a three-dimensional space so that this Green's theorem can be interpreted in Stokes' theorem, right? So we had a three-dimensional thing, but we embedded it into two-dimensional space, but still this vector field and n is the three-dimensional vector field. But we can use the same Green theorem, right? So here, if I rotate my orientation, then this normal direction, which is the orientation of new space, is 0, 0, 1. This f, whatever that is now, let's say, originally, if f was p, q, r, then it now becomes what? P prime, let's say q prime, r prime, some combination of p, q, r. If you take the rotation, then it's not become a totally different function. It's just a combination of p, q, r. Anyway, so when you do that, so you have a vector field, but the last part doesn't matter, right? Because okay, well, let's see. Well, let's apply this to this situation to the Stokes theorems before we move on to the Green theorem. So let's try to apply to the Stokes theorem. Then this is going to be, let's say, this is delta s, okay, or delta s prime, or so on, and this is c prime. So the line integration over this c prime of a vector field f ds is equals to delta s prime and what of f n, well, in this case n is 0, 0, 1 ds, right? So we want to show this. We want to show this. But think about the left-hand side here. We have a vector field which has three components, but we only care about the curve which lies on xy plane. So the direction, there's no z direction to this curve. So if you write your line integral in other format, it's going to be p prime dx, q prime dy, r prime dz, but there's no dz component on this curve because we made this c prime to be flat on xy plane. So this is 0. So we only have p prime and q prime. So this is equal to the line integral as if you have vector field whose third component is 0, okay? So this is equals to the line integral of p prime q prime 0 ds. All right, so that's the left-hand side. Let's think about the right-hand side here. So that's going to be delta s prime, the flat plane here, and we have r prime, because only that r prime is survived. So this is ds, okay? Now, this is just a scalar function, all right? Think about where you got this r prime from. So we are measuring the quantity of this vector field of the n component, okay? So we are taking a projection of this vector field to the normal direction here. That's exactly what you get when you take the project f to the normal direction before you take the rotation of this planar plane. So this is actually equals to that, okay? All right. So before I move on, we want to show this. So this is what we don't know, but on the left and right side, in separate way, we know that what we want to compare is this guy and this guy, okay? And now let's look at the Green's theorem, okay? All right, so in the Green's theorem, it says that if I have that integration here, so although it's a three-dimensional vector integration, but it is equal to the line integral of two-dimensional vector field because there's no z component at all. So as if I'm taking this curve C in two-dimensional plane, then is p prime dx q prime dy equals to what? Integration over d of rotation of this q prime x minus p prime y of dx dy, right? That's what Green's theorem tells you about. And then remember that what we are doing here is over a very small region, okay? And because of that, we assume that this n and f are almost constant, okay? So this p prime and q prime is simply almost a constant. I mean, it's, well, so not that p prime and q prime is actually a constant, but we can assume that this is almost a constant value. So whenever you take the partial derivative, the result is also almost constant factor. So we can say that this is equal, almost equal to what? This can be just constant scalar here. So qx prime minus py prime times of the area of D. So area of D, let's say, is equal to delta S. Okay. So that's the left-hand side. And let's think about the right-hand side here. Okay. So F n delta S, this is just the area of S, okay, delta S, is equals to, well, there's a normal direction here. I don't know what this direction is. I'm not going to give a component for this n and just use the fact that this is the component that I'm get f, the n component of the vector field f. Let's see. Let's think about. Let's think about this situation. So, all right. Okay, so all right, let's think about a little bit. Give me a little bit time. So rotation. So let's see. Qx, Py, F, and N. So let me trace back what I'm trying to do. We want to find out these as equal. Okay, that's what we want to do. So we want to find out that these two are equal. So how to make that equal is I'm going to use the Green theorem on this part to get this quantity. And I'm going to show that this quantity is equal to this quantity, which is the right-hand side of this equality. So then I prove this equality, right? So that's my plan. And what I'm worrying about is that I'm taking an n-directional component of the vector field, okay? N-directional vector component. Sorry. So I made a mistake here. Sorry. This is not the Stokes theorem. This should be the curl, right? Yes, cross product. Sorry.
So I was worrying that if we take the both part, then the whole integral will be 0. That was my previous concern.
Yeah. That's my also concern. So anyway, so we had this. That is for the flat plane, right? That is for the flat plane. And this cross product, so this F is this guy, right? So, right. Okay, so then that's fine. Okay, that's finished. Okay, so, yeah. So this is equal to surface integral of cross product. Oh, let me rewrite this. So we are taking about F, but after rotation. So we are taking P prime, Q prime, R prime, and surface integral over this flat surface, which orientation is 0, 0, 1. So the last component of this cross product survives, and all the other disappears. The last component is that Q prime x minus P prime y, and that is taken over as DSS, delta S prime, right? So that's the right-hand side. So we are actually done, right? Because we assume that this delta is so small that this is almost equal to qx times py prime delta s. Okay? So then we are done. So Green's theorem tells you that the left-hand side is equal to this part. So we basically proved that this is equal. Okay? So let's go back. Let's go back to the original case. So we were talking about this boundary on the flat surface, which is oriented, which is rotated, or rotation and translation, if you have to, of the original piece of surface S. So what we have done here is that the curve C, along the curve C, when you take the line integration, is equals to, let's say I put the delta S here, so meaning that small piece of line boundary, over this and cross product of F. And then you take the surface integral. So think about, so this is after rotation and translation of your piece of surface. Okay, we prove that this equality is true when you transform your piece of surface into the flat surface in xy plane. Okay, that's what we have done. But think about the meaning of these two. Okay, what you have done in the left-hand side is that you try to calculate the work done along this boundary. Okay, so does it really change the work when you have a vector field on the three-dimensional space and you have a curve, bounded, a closed curve, and try to work done by the vector field along this closed curve? Whether you put your x, y, z axis in this orientation and that orientation, does it really change your work? No. It's just perspective. X, y, z axis are just way you express your function in a simple way, and it doesn't change the absolute value of the vector field. So what we have done to translate this piece of surface to this piece of surface is just rotation and translation. It doesn't change the value of vector field. Okay? So the line integration is same after or before you rotate and translate. And also you think about the flux. So you have a curl of a vector field, and you try to find the flux of that curl of a vector field. It doesn't change when you move or rotate your surface, because moving and rotating your surface is same as moving and rotating your axis, x, y, z axis. The total amount of flux doesn't change by looking at which different perspective of your surface. So this happens, this holds true for the surface delta S before rotation and translation. Okay? So think about carefully what we have done. So we try to make the small pieces as flat as possible and try to put in xy plane so that we can use the Green's theorem. And the Green's theorem proves that these two quantities are the same. Okay? So we can trans back to the original three-dimensional surface so that we can say that this equality is true for every pieces of this surface. Now, let's make a big picture again. And I made a subdivision. So I make a big subdivision just in case. So for each subdivision, I know that if I take a line integration in this orientation and with according to that orientation, I have orientation of surface to that direction. Okay. So then here I have line integral equals to the surface integral of a curl of a vector field to that direction, okay, on here, okay. So let's say I put an index here, so Cij, Sij here, okay, but assuming that this piece is indexed by I and j. So let's say I did the same thing with the next piece. So let's say here. So, okay, so maybe this piece has 5 boundaries, but it doesn't matter. So I take the same orientation so that I have the same orientation of the surface here. So that's my n direction. And I do the same thing for here. So let's say Ci plus 1j here, closed line integral here, and then Si plus 1j of the surface integral of curl ds. And what happens is on the side which shares with by the two regions here, I have computed a line integral on this direction for the red curve and opposite direction for the yellow curve. So if you take the line integral in the opposite direction, it will have the negative sign each other. So if you add them together, it cancels out. So it happens to every other regions. Every side that is shared by 2 regions will cancel it out. So if you add all the left-hand side, what happens is you only left with the line integral on the boundary of the surface. So this boundary, okay, so these boundary only survive after you add these whole left-hand side. So basically you are left with the line integral over the boundary of C in this orientation. And what happens to the right-hand side here? Right, you sum up all the surface integral of the curl, right? So if you want to be a little bit more rigorous, then you can assume that this is almost equal to the constant vector field given by the curl of f over the area Sij, and then you sum this over, and then you take the Riemann sum to find out that it's equal to the surface integral of f. But anyway, that's the entire. So if you add all the fluxes for each pieces, then you take the flux over entire surface of this curl. Okay? So that's why this Stokes theorem makes sense. Small pieces follows exactly what we have observed in the Green theorem. And because of that observation, each pieces have a flux approximately equal to the rotational vector, the line integral of a rotation, surface integral of a rotation of this vector field, which is the curl in this case. And then you add all up together. Whatever remains is the line integral over the boundary of this surface, and then you're adding all the fluxes. Yes?
Well, the key point for Green and Stokes theorem is that 2 things, I think. Inside the offset of the inside of the curve, and the second thing is that only the edge of the surface or 2-dimensional or 3-dimensional surface are the remainders, so that we only care about the remainder, the edge of the
Mhm.
surface, right?
Mhm.
Then the both Green and Stokes theorem is a little ambiguous to me about the edge of
Mhm.
of their curve,
Mhm.
because we actually divide it into the parallelogram
Mhm.
shape, right?
Yes.
But at the edge of the curve, it does not really fit exactly to the shape of parallelogram.
Right.
In that case, in this case, we just follow the curve of the edge,
Mhm.
but actually if we follow the preconditions that if we follow the path that we divided previously,
Mhm.
then it should be
So the question is, if I interrupt, it's okay to interrupt. But the question is, if you subdivide the surface, inside could be a parallelogram, but the edge of this surface could be not parallelogram. And how can you use that as fit into this argument? And one answer is that even though it's not a parallelogram, it could be some polygon, right? Flat polygon. So you can use the rotation and translation to put that in xy plane. Okay. And also another answer is that so whenever we try to subdivide our surface, I was trying to think about this picture. So you have a parameterization of a surface. So if the parameterization is defined on this rectangular domain, then it should be always a parallelogram shape for each pieces of this subdivision. However, if you had a non-rectangular domain for your parameterization, which could be very possible. So let's say we have a domain D, which parameterized over D to the surface S. Then what we can do is, okay, so if I make a grid here, then this one will be a map to parallelogram. But if you're looking at these pieces, it's not a parallelogram, one-to-one parallelogram. But if you try to enlarge and enlarge and make a smaller and smaller subdivision for the rectangular subdivision for D to approximate the area of D, then you can use this whole rectangular region to map to the surface S. In that case, what happens is that, in fact, you have these region, but you kind of approximate that by some parallelogram shaped surface, which have an extra region here. But if you subdivide more and more, this error is disappear. So that's one way you can think of. So any other questions? Okay. So I don't put any assignment about the surface in the Stokes theorem and divergence theorem. Because it's up to you to put your own questions about these topics. And if it's an assignment, then if we are obliged to answer some questions and we try to show off, which means that we try to write which we don't understand. So my intention not to put an assignment about the Stokes theorem and the divergence theorem, even though it's a very important subject, is that I want you to really understand on your own pace about these two theorems, and then also on your own understanding, not to make anyone else to convince that you understand well. It's important to you to understand, not convince other people to show that you seems like understand. Okay. All right. So we're going to stop here. And again, let me announce that this Friday is the deadline for every assignment. So fill out the assignment questions for the questions and programs and project. So about the project, don't make a big subject, don't make a big topic. Just make your goal very, it could be really tiny goal, okay? So tiny as it is, concrete, make it concrete, okay? So make your argument concrete in the beginning to the end, okay? And what else I should say? By the way, so the grading component, the in-class activity is by the question section, okay? So if you answered my basic questions completely, then you should have full marks on in-class activities. And for the programming questions, if you follow what I've shown in the classroom about the programming, even though your code doesn't work well, if I see that you try to write whatever I've been showing to the whatever I've been shown to these questions, then I will give a full mark. So let me show you again. So whenever you try to put your this is show. Okay. Whenever you try to put your code, don't copy and paste your code. Okay. So let's see. If I go to this programming part, so you should embed your code in Replit. So maybe I show you some template here. So here, where was it? So maybe I put that in week 5. No. Maybe week 6. No. I think I did somewhere. Did anyone did similar? Okay, so let me go here. Okay. So not yet done here. I erased the test one. So maybe let's look at this one. Okay. I think I showed you before, but I want to show you it again. Okay, so here's one. Okay. So you see, this one already has the result. So you can, this is one, you can simply copy and paste, but that's on your own choice, whether you do that or do it on your own. But anyway, so this is how you should do. So this is the template questions, and you probably copied to your Notion pages. And The above is an instruction, and what you have to do is, under the result, you have to embed your Replit page. So you simply copy or paste the URL of this Replit page. You have to register and log into the Replit to use the Replit. And you paste, then there's an option that you can embed the Replit page. So this is how you should done with the code. So work at the Replit, or upload your code to the Replit, and then try to embed that page, your own page, to this Notion page. Okay, so there is a code. So this way I can actually navigate your code and then see the content of the file. So there are no other way I can actually trace back how you do it and then how this code runs. So this is the only way I can grade your work. So feel free to use this as your instruction. So this is where, okay, so this is on the second programming assignment of the template page of our portfolio. Okay. All right, so let's call it here, and then see you on Friday.